Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellyn, Illinois. And this video is going to take a look at the C++ programming language, and we're going to take a look at exception handling, so like try, catch, and throw operands, operations today, and also function templating. And at the end, we'll talk a little bit about looking into the standard template library, like a quick little introduction. And we'll have plenty of time for all the other parts of the standard template library. So this is just a very, very high-level description right at the end here. So I already have Visual Studio up and running, and I'm ready to kind of go through the lecture notes. So the standard template library extensively uses exceptions in certain places. The standard template library tries to use speed over exception handling, which would be a little bit slower for the most part. But you will see as you go through that sometimes you can avoid these things and sometimes you can't, so you have to understand them at least before you can push forward with this kind of stuff as we move into the more advanced topics. So yes, an exception, something unexpected has occurred. Maybe a file didn't open correctly, or maybe you've accessed somewhere in an array you're not supposed to. Something you're not supposed to normally do that's outside of like the thing a warning or a compiler error can give you. But the cool part about this is that when you throw an exception or you catch an exception, you can handle that exception however you see fit. The people who wrote our libraries, the standard template library, the boost libraries, you name the library, they can't anticipate all those years in the past when they wrote the code how you would want to handle that error when it comes up in the future. So it's up to you to decide how to resolve this thing, and you'll see how we talk about this. And it could be as simple or complex as your program requires it to be. If a video game sound effect doesn't play a horn, I think you should just let it silently fail. You know, it's like we don't need to stop the whole game because a horn didn't sound. But if I'm trying to process credit card transactions or something like that and something goes wrong, it's not like you're just going to throw up your hands and just go, I tried, and I guess we don't need to charge those people for all the charges they made for that day. Wouldn't that be wonderful? But that's not how it works. The exception gets handled, the technician comes in and figures out what's going on so they can progress through and process your credit card record. And so there are different keywords that we can start using to account for these kind of things. So let's see, we have exceptions, we can throw an exception, we can try to run code that may throw an exception, and then we can catch errors, exceptions when they occur. And so you can see an exception can be an object, it can be any type, but I'm going to show you guys type exception, std::, exception exclusively here. And you can throw them yourselves. You could create your own library and say, if this thing occurs, throw an exception. And someone will have to fix it, or else, as you'll see, your program will halt. And then you can say, okay, I've tried this code. If something goes wrong, here is my catch. Here are my handlers. This is what I want to do when things go wrong. So these are my three big keywords. So let me set up a vector real fast. Vector of ints, and I'll just call it v, and I'll just put a couple values in. Okay, and then what I'll say is there's an at function, and I'll say cout, and I'll say v at the 9th location. Or I'll use the at function at the 9th location. Or no, I'll use square brackets. So this is definitely out of range, right? I need to include vectors. Okay. Okay, so I got vector. I've got all this going on. Give me the element 9. What does it do? It actually gives me a debug assert. Assertions are different than try, catch blocks and exception handling. There's no way to fix this kind of problem if it comes up. And so you're like, well, can we write some code to handle this? We can try, literally and figuratively, to try here. And so let's see. Let's talk about this. So you have if, throw, this kind of stuff. But what we can try to do here is say, okay, let's try this code. And then if something goes wrong, I don't know what to do. Let's try to maybe print out, there's a function inside of an exception called what. And let's see if this fixes that. And lo and behold, it does not. As I was describing, assertions are completely different than anything else. This appears to be a vector subscript out of range because we expect that. And so, yeah, this is not a good thing. But what if I just change that to at? And if you don't understand, say later videos will show everything there is to know about vectors. And so we can discuss these details at a later time. But just if I run the program now, you can see I get a completely different result. My program didn't crash, and it actually prints out invalid vector subscript inside of the catch block because completely different mechanism was used here. I tried to run code that I knew might throw an exception because I'm just saying I know that the at function throws an exception if something is out of range. And then if I throw an exception from here, I can catch it down here. If I forget a catch, well, first of all, if I just eliminate the try-catch altogether, this will still throw an exception and the program will halt. And there you go, because unhandled exception. And basically what will happen is everything tries to unwind. Your whole stack tries to unwind, try to find somebody who's willing to go in and fix this error, and there's nobody to do it. And so that's where the program just halts. But this mechanism allows me to go around that and say, okay, try to run this code, and if something goes wrong, catch the exception and do this with it. And here is where you can do whatever you want to do. You can halt your program. You can do nothing. In this case, I'm just printing out the error message that pops up when this occurs. Again, which is the invalid vector subscript. Okay, so we've already discussed try-catch, and so you just have to get used to when you're writing code, figuring out, well, which functions am I using? Do they throw exceptions? And if they do, how should I go about handling it? Because as much as we'd love to think our code is perfect and the world is a happy place, something will always happen. There'll always be something. And so user input will come in poorly. Someone uses your program differently than you expected to. There's a lot that can occur. And so, you want to make sure your program is as foolproof as possible. Okay, so let's see. A function that throws an exception is called from a try block. Okay, yep. This can throw an exception. So what if I just do this? If I put a 2 in here. We haven't tried that out yet. And I go, this one actually prints out the number 3 instead of the error. And that's because there was no exception thrown because this function is perfectly legitimate. If I use this and it finds value 2 and it prints out the 3 and then it continues on and there was no error to catch, so it went around and then the program ended. So it goes down completely 2 different complete code paths. But if the error does pop up and an exception is thrown, it immediately falls down to the catch and tries to handle this. So just to say, if I try to say this, it won't print, it just stops here. It's like a return, basically. It kicks me out of the try block immediately when an error occurs. And so you can see invalid vector subscript. It doesn't return back. It doesn't fix this and then try to return back. You would have to write code to handle that. You're just trying to say, try to run all this code, and at the first hint of warning, kick out and let me catch what's going wrong. So we can also throw exceptions, and like you can see this here. If this is just a function that goes, okay, how many total days are there from a number of days and number of weeks? And you're like, well, if the number of days if it comes in as a negative number or greater than 7, well, then I can throw an exception and just say, this is not right. And so just to say something like, I don't know, just have a function. All right, do a little better job. Double, square root, double. And so just to keep it simple, I'm not going to figure out a square root function. I'll just return square root of x. However, this is my opportunity here to, if I wanted to, just like they have here, I can say if x is less than 0, then I can go ahead and throw an exception. So I can throw an exception, and I can put inside of here, it's an object like any other type of object. And so you just have to get used to how to use this thing if you want to. Const care pointer, and then just whatever else here. So I could just pass in a string and be like negative square root not allowed or something like that. And so that's my exception. And so I could use this just like anything else here. Now this thing can throw an exception. So I should, in all consciousness here, as long as I'm, for as careful as I am, this thing can blow up on you at any notice. I just have to pass in the wrong value somehow, some way. And so coming back to here now, you could try this, and you'll see out square root of 1 with an end line, and then just try this a few times over, 1 and 2 and 3 and 4, or just 1, 2, 3, that's fine, and then we can try this, and I can try a -1, and then we can print out whatever comes up. And so, yeah, if I just print out 1, 2, 3, 4, 1, yeah, everything will come out perfectly fine, because all 5 lines of code are values that are greater than or equal to 0, so it'll fall through this if statement and it'll return the square root, and everybody's happy. But again, coming back, well, what if I add any negative value? Now everything kind of halts immediately. And now you see the second I hit this exception here where square root of -4 occurs, the exception gets thrown, it comes back to main, main kicks it down to the catch, and now it prints out that, and it just stops. Notice it doesn't finish up. It doesn't do this part. Because it catches that exception and falls straight through. And so that's pretty much, that's pretty much exception handling in a nutshell. It's just, again, when you're using other people's code, you kind of have to look through the documentation to see what functions throw what exceptions so you can make sure you handle them when things occur. And so let's see. So say, like, we've tried the different ways. This is pretty much not going to make you do anything crazy for this. When I was out in the field, we used what are called asserts. You'll see asserts in this course a little bit. I just show it to you, in a little bit of an offhand manner. Again, it's just a completely different way of doing things than the try-catch block association here. And so they're using a try-catch block for this program if I'm just going to divide two numbers. Because a divide by 0 can halt my whole program. It's a hardware divide by 0. And even if you divide by 0 with floating point math, you're still going to get just infinity or not a number or some garbage result. And so in this case, enter two numbers that are going to be divided, a into b or num1 into num2. But if, like I said, try to do this, try to call the divide function that does this job, and it kind of does what we're doing here and says, hey, if the denominator is 0, throw an exception. In their case, they're throwing a string instead of an exception object, which is fine, but otherwise they're static casting and returning and doing whatever they have to do. And so again, if this fails, it'll catch and it'll print out the exception string. And then if it doesn't, it'll do the work and go around. So that's perfectly legit. So 12 and 2 is 6. 12 and 0 cannot divide by 0. And so again, that's just a good another example of just what's going on there. And just taking this step by step, and then when you hit an error, you fall out like a return, basically, or a break, if you want to. Let's just think of it more like a break. And if you go all the way through, you just work your way right around that exception handler, the catch block. And so this language, I don't think has the word finally in it. Does it have finally anymore? I guess it does. Like I said, we're not going to worry about all the extra little details. We're just basically covering, because there are little things that can go wrong, but this isn't the time you can deal with that in your later adventures in C++ programming. So again, try-catch. And just for the record, for those of you watching this video, this doesn't mean you put all of your code now in try-catch blocks and now all your code just becomes just these nested try-catch blocks. Again, these are just for specific situations where things can go catastrophically wrong. They're not meant for just little tiny errors. They really aren't. And so, let's see. So new can throw an exception. Even just newing up memory, dynamically generating memory, right? If I just go while true, new. While true, new double. And so let this thing run and run and run. It's taking up 8 bytes, 8 bytes, 8 bytes, 8 bytes, 8 bytes. Come on, how long does it take? How long does my machine take to crash? We'll find out. But new, let's say, just the things you take for granted. There we go. Unhandled exception, bad alloc. Because I kept newing up memory. It's the fastest giant's memory leak that you've seen in a long time. Because I keep taking and taking and taking memory and not giving it back. And so since I'm doing that, I'm eventually going to run out of memory on my machine, and that's an exception that can be thrown. So I could throw this in a try-catch block. And so instead of my program halting, I do this again. At least the exception gets thrown, and what will it print? It will probably print the bad alloc. Let's see what happens. But at least it won't crash anymore. There we go, bad allocation. So the program, I can maintain my program. I can still run my program even though I'm out of memory. And so maybe I'll still halt my program because I'm out of memory, but at least It's up to me what to do instead of up to the computer just to throw up its hands and just quit on us. So let's see. The value that is thrown does not need to be used in a catch block. Notice there was no try or catch in this function here because there's no way to know how I want to handle it. This is basically a library function that I'm creating for whoever later on down the road. And I don't know. Do they want to silently fail? Put an error message? Halt the program? Anyone, all of those? I don't know. Any and all? Or others? And so it's not my job to think out what they want to do. It's just my job to say, hey, something went wrong. Throw up a flag. And just say, something's wrong. Fix it. So that's why you don't see any catches here, because there doesn't need to be, because the throw kicks me out of this immediately. And so what's interesting here also is, like if an exception gets thrown, exception is the base class. If you want to look through the Jasudas book, there's a little section in there somewhere that shows you the exception class and all the derived classes. So you can work it down and say, like, because that handled a bad allocation, right? Something like that. But what about out of range? Like an out of range exception is an exception. But what would happen? Because bad allocation is not part of out of range, or is it? Let's find out. I wish I could make it crash harder and faster. But let's see what happens. And there we go. I tried to catch it, but I couldn't catch it. The catch block didn't catch that specific exception, the bad allocation. It tried to catch it. It would have caught an out of range error in here, but that's not the kind of error. So you have to watch out. So exception is just basically your catch-all, because it's like, like this exception is anything that the standard template library can throw at you. And so a lot of times if you have it where you can have 2 or 3 different things go wrong, you do not want to catch it this way. You want to handle those 2 or 3 different ways with 2 or 3 different catch blocks. So you can have more than one catch block after. And the same goes. If I find a catch that finds the type of exception that was thrown, it'll fix it using whatever you put inside of here. However, if like anything else, if it doesn't find the type of exception in here, it will keep on pushing on and keep pushing the call stack back, trying to find someone to solve it. And if it can't, it halts the program. So again, this is exactly that. If an exception isn't caught, even, it has to match the type, it has to follow the inheritance is a relationship when it comes down to, is this thing whatever type, a string or an int or an exception or an out of range or this or that, the program will terminate if it can't find a suitable match for the catch handler that's going to do the work. And so we're just showing here, they were throwing you can throw ints and strings and all sorts of stuff. I think it just makes sense to always use just exception. And if you need to, you can override. That's the cool part about exception. I don't know, it's always quick and dirty here, just to take a look at this kind of crazy stuff under the hood. And I see, like I said, it's all just gibberish to most people, me included, almost all of this. The only thing that screams out non-gibberish is the fact that you see the keyword virtual with the destructor, and that tells me that it is a base class and it expects me to override that behavior. A virtual destructor, as we've learned from previous slides and previous videos, virtual destructor screams out base class. And so the exception class is no exception. So you can redefine them and you can derive from exception and do whatever the heck you want. And I've done it a few times, but it's not a common, it's not always a common thing depending on what your job site and everything else. Okay, so, yep, and we said a class can have more than one exception class. You can go crazy on this stuff. And so you can say they've defined a negative size. They didn't derive it from exception, but they could if they wanted to. And you could see negative size is the type that gets thrown. And so here, throw negative size. Throw that negative size exception. And then where's the catch for this thing? Here's the try and here's the catch. If you can catch this negative size exception, then print this out and then say end of program. So everything's happy. As long you put positive values in, you never see any of this error catching code. 10 times 20 is 200. But if you put a negative value in here, you go down that alternate code path, and you will now print out and go down the code path that relates to the TryCatch, and then specifically the catch, and there you go. And say you still resolve the problem, and the program completes without a halt. to the thing. And so saying once the exception is thrown, the program cannot return back to the throw point. So we were saying, like you say, it hits this, it prints everything out, it doesn't come back to this line of code after it handles. It's done. So if you need to reloop, like if it's input validation or something like that, like like if I'm asking you for a number between 1 and 100 and you enter the word Brad, then yeah, there's going to be you have to basically loop this thing around. You have to worry about it on your end. You can't just rely on the programming language to take me back. Because realistically, how would it know which line of code threw the exception? How would it know where to put you back? Part of it is it's too complicated to do, and part of it is it really doesn't gain you anything anyway. And so you got to watch out though, because things come and go, right? If I hit an exception here, if I had a pointer, if I int pointer a equals new int, well, what happens, right? This is the fun of this. If I new up this guy, and then this new, and don't mind the memory leaks, I'm just doing it on purpose, but if I hit a crash or an exception and I come out, this thing's going to memory leak on me because there was no way to delete it. And so that's the thing. We do have to be careful with dynamic memory and that kind of stuff. And so it's not all, most everything else gets destroyed like anything else when it comes to scoping rules for just statically casted variables. But for dynamics, you have to be real careful in a try-catch block with this because you have to fix this up somehow. You have to undo the damage if you end up in the catch. Otherwise, you'll have a memory. You can nest try blocks together, and this is where I say, this is done. We're done talking about this. Like everything else, you can nest loops and loops and all sorts of crazy stuff. You can have blocks inside of blocks inside of blocks. But after a while, you start wondering why you're doing things that way, and then you start thinking there's got to be a better way. Okay, so moving on. Function templates, that's the other major topic of this video. I have gone ahead and started and created a function for absolute value. And again, absolute value for a one-dimensional number is just how far from the origin point it is. So if it's negative, you just turn it positive. It's just, it's the magnitude more than it is the negative or positivity of it. So very simple function, and I made this for int. And so a function template is something that we can make into this thing, and I believe you could trust me if I say, okay, give me an absolute value of -3 and it'll print 3. It's simple enough, right? There we go, there's my 3. And so, you could test this into your heart's content. I'm pretty confident in it just as it's written. But what if I wanted to do this for other data types? Okay, here we go, right? So I got int, I got long. You're like, oh, that's great. How about character? And how about short? And how about double? And how about float? And how about double, long double? And how about this? And how about that? And everything else. And then they ask you, well, what about things that are going to happen in the future that you don't even know? We might even have a new data type in the future that's beyond long and long, long. Who knows? And so you're like, well, I'm not wanting to think about that today in 2020 when it's a 2030 problem or something like that. How would I know? And so the function template idea is a way where we can, instead of writing hundreds of functions or tens or just more duplicate functions, because they all do the same stuff under the hood, right? All the code is the same. It's just these data types that are different. And I don't want to go ahead and overload all these functions. And so you found a pattern here. The only difference is the data type, and that's truly it. And so when we write this, the parameters. So this is going to be different. We use parameters like in functions, but we can also use parameters for data types. And so you'll see here. We'll say this now, and then maybe it'll come together in a minute. When you call this thing, the compiler will generate the code for the specific data type that you've templated. And let's see, do they have an example here? Yeah, I can use this as my example. They have a times 10 example. And so I can go ahead and say, I'm old, so I use slightly different syntax than they use. And so I use template, and I use type name T. And this T can be anything. We just conventionally use T for type. And so this is basically yelling out, this is a templated function. And you have to put this and type name is exactly the same as class. They're interchangeable. And type name is just the way I learned it. Class is the the newer, more modern way, but they're both acceptable. And so now it's just a matter of going through and figuring out, do I need to modify any of the variables types to make this thing more generic? And the answer is obviously yes, because now, yeah, this thing's broken, of course, because now it's absolutely, whatever, we're fixing, in the process of fixing this thing up, or are we? Isn't that interesting? No instance of function template ABS matches, just because I got this little tiny bit here. But we can fix that up in a minute. But you're saying, okay, if I'm going to take T, and like, let's see, are they using it anywhere here? So that, yeah, they do it here. T is the type that comes in, and T is the type that comes out. In our case, int comes in, int comes out, or short comes in, and short comes out, or float comes in, and float comes out. And so we can apply that the same way and say, whichever type you give me, I'll make it work. This is weird, right? You know, it does take a while to wrap your brain around, and like I have a book fully on templating and get to about chapter 3 or 4, and my brain just melts, because templating is just can be just a crazy, crazy idea when it comes to how to create generic functions and how to get these things to compile and run. And so that fixed our compiler error down there, but I can also alternatively do this. And this is the beginning of, you know, you've seen this before. We did vector of this earlier. The angle brackets indicate template. And this says, okay, treat this absolute value function like an integer, keep t as an int, and then convert -3 into its absolute value. Or I can use it as a float. And I cannot use, the only thing is I cannot use, whatchamacallit here, I can't use debugging for this because of the way this works out. It actually won't tell you the t-type while you're running and things like that. Because again, what's happening under the hood here is every time the compiler sees that, okay, absolute int, it generates the function for the integer version. And then it'll actually make a second version of this absolute value function for the float. And so now there's two separate versions, and it knows which one to call. It knows to call the integer version, it knows to call the float or the short or the this or the that. And so this should print out exactly like you expect. And there's my 3, there's my 2.87. And just to prove it's an int, even if I put -3.3 or something in here, you see it still comes out as 3 because because it does what it needs to do to turn it into an integer value that comes out. Even though this came in as a double, I'm treating it like an int. I should put an F here just to be safe. Just to be sure, there we go, same deal. 3 on the integer side, 2.87 on the float side. And that's exactly what they're doing here. Every type t that can handle multiplication can use this function now. Just like any class t, any type t, that uses the less than operator and defines equality and negative, like a negation, can handle this. And that's weird because we start creating our own classes, which we've already been doing in previous lectures. And if I want to use this function for like a werewolf, what is an absolute value of a werewolf? I don't know, but if we needed to do something like that, I would need to define the less than operator and the negation operator. Otherwise, I'll get some weird errors. That's the thing using the standard library. When you get some errors, you get some really, really weird errors. You really do. And so they used it the same way. You don't always have to. The compiler will try its best to figure out what's going on. But in this case, if I get rid of the templating, and I just say absolute value -3.3, I'll get 3.3 out of it. Because it knows that this is a double, so the compiler will try to turn this into a double version of absolute value. The t-type is double, and that's why it's a little different than if I explicitly say, wait a minute here, I want to treat this like an integer. And so, again, they have an int version and a double, and it works fine, and it knows which one to call. It just knows. And so we can do, say, templating is a crazy thing. We can have multiple template types. So for something like this, where we can have miles and gallons in different types, so we can, whatever that means, ints and floats and shorts and you name it, this presumes that you can have different types for the miles and different types for the gallons, and somehow it'll just work out in the end. So just to say you can have, there's no need for this function especially, but for this function or something you might want that. And this template library does this quite a bit. And let's see, if I include, just real quick here, include the double-ended queue, which we'll learn about very shortly in this course, and I create one. And if I put a comma here, you can see there's two different types here. So there's the type name of the double-ended queue and the allocator. And we say you can actually have templates, like you can have default templates. That's why it says there's a default equals allocator. That's why we don't have to worry about it when we set up a double-ended queue of that. Or if we set up a vector of ints. Can I do anything after? Yep, I can change my memory allocator if I want. But it's defaulted to me not worrying about it. That's why we never thought about it before. So we can do that. We can have multiple types together, and you can see the powerfulness of this because we can just write the code one time, right? We did this in 10 seconds once we knew what we were doing. And then after this, now we can use this thing forevermore in any class now and in the future that needs to use this. And so let's see. All data types specified in the prefix must be used. I think that's where I was getting that error earlier. It just came from the fact that I called out to use a t-type, but I never truly used it in there. I just had int for these two. That's probably what was happening. You know, like all these little rules that pop up. Function calls must pass parameters. It must pass an actual parameter for the data types. Can I just do absolute value 5? Can I do that? No instance of function apps matches the argument list, which just takes in a double. Nope, it can't handle that. It just can't. You could try, say, is it fun to experiment or is it scary to experiment? It depends on it. Sometimes it's fun, sometimes it's scary. But again, it's weird. Just, regular functions, function templates, you must define them before you're called. Yeah, all these little details. But one interesting thing here is if I introduce a compiler error, I think we can all agree that's a compiler error. And if I build this thing, you will notice, oh man, it worked this time. Sometimes, let me just say, sometimes you can do these kind of things and it will not give you an error unless you try to actually use the templated function. In this case, I got slammed. Sometimes you don't, and it really sucks because you write your code, you always presume the compiler is there to help you, to figure out if things are going wrong, if I need to fix up, if I have a syntax error. But sometimes, this is not one of those times, that even if you have an error in a templated function, until you go to use it, because it's a template, you're not generating anything until you try to use it, that's when the error message will pop up and go, hey, something's wrong here. But again, in this case, that didn't happen. Okay, so a couple little last things here. Again, a function template is a pattern, right? It's an algorithm that can be solved with different data types that doesn't require me to change the underlying logic. Sometimes that's not always true, but in many of the cases, and at least in this course, it would be very true that there's a pattern that we're solving. And like I just said, no actual code is generated until you actually go ahead and try to instantiate it inside of code somewhere to try to call this thing and use it. And so because of that, if you do not generate the function, it requires no memory. So that's kind of cool that you could have a function sitting around that actually just sits on the compiler side and never makes it into your final program. And when it does, it only does it in the ways it is needed. It doesn't generate every possible confirmation for ints and floats and shorts or whatever and just hope. It only generates what it needs at the end of the day. And as I was showing here, when you pass this stuff in, make sure that you've defined the operators. Let me just real quick here, I'll say class A. This is it. Boom. Just create a class real quick and say, okay, give me an absolute value of A. And I can't do it because it says, first off, no, okay, oh shoot, negatives. Hold on, okay, let me do this. A, boom. And try to whatever, absolute value, sure. Now you'll see, now you'll see this. And that's what I'm saying, like, I'm not defining any of these operators. Well, first off, that one doesn't work. Here, let's just say, if A goes in, A comes out. Let's see, let me just change this up. That's not the error message I was expecting. But this class doesn't use the output error, the output operator. But here you go. All right. So as I was saying, this getting to a point, sometimes these more complex things, takes a little while to get there. But the negation operation is not defined for class A. So negation and less than, and then when it comes down to it, a minute ago with the print, it didn't have arrow arrow or like the stream operator. So if I wanted to do this for class A, where I can define absolute value, I will need to define what less than means, I will need to define what negation means, and I will need to define what print means. It's a lot of work. And it kind of shies you away from doing it I don't know if that's for a good thing or a bad thing, because it's just, it sounds like a lot of work, but it's just overloading a few operators. If you've done it a few times, it's tedious, but it's always tedious, especially that output operator with all the stuff that you got to put into it. Okay, so let's see. So the rule of thumb for getting this thing going is kind of how I already did it. Like, you don't start out templating right away. You get this thing working for one of the data types, and then you work it through and go, well, how can I make this more generic? Because if you start out making it generic off the bat, generally you're going to have more trouble. So again, last time here, templates are appropriate for multiple functions that perform the same task with different data types. Okay, duh. That's a given. And so we developed the function using the usual data types, just for we picked int and we made it work for ints. And then we add the template, and then we go ahead and look through and convert. But in this case, everything converted into something else. But that's not always the case, right? Just to say, that's not always what could occur. What if I was searching a vector, and I want a vector of type t, which t could be anything, and what if I wanted to return how many values of a certain type were found? So let's see. Let's just write int here, and I go how many in vector, and I will pass along a const vector of, in this case, a vector of ints, reference, call it v, and I'm looking for this value here. And I'll say, how many times did I find this? I'll call it finds equals 0. I'll return finds. And then in this case, for every int I that's part of v, if I is equal to value plus plus finds, right? How many times is a specific value in a collection of data? Okay, so with that said, without even testing out, we're pretty confident in this, right? We have a constant reference vector. It's of all type int, so I'm turning this into an int. I'm doing all the work. I'm checking this against the value, incrementing and returning. So this should be pretty good when it comes to working it out. Oops. Oh, hold on. Let me get rid of all this A code here. This garbage code. Okay, let's try this again. Uh-oh, I have a warning. Oh yeah, of course, because I'm trying to turn a double into an int. I was just proving a point there. That's why I have that warning. But coming back now, if I want to, I wrote this out. So I could create a vector and just do it real fast. Okay, and then I can see out I don't even remember what I called this thing. How many in vector, and I can pass along v, and I could say 1. And I can go ahead and I go 9, because that's how many 1, 2, 3, 4, 5, 6, 7. There are 9 of them in there. Oh, sorry, you don't see it. There's my 9 right there. It prints out the 9. And so, yep, it worked for the integer type, and I'm very happy with this. So then just to finalize this, I could say, okay, let's make this a template. So I can pass in any type of vector, not just type t. So I go, okay, template, type name t. But again, all of this is just to say, the integer value should stay the same, because I'm not going to return a t type. I'm not going to return a long. I just want to return an integer that tells you how many times you found the value. So not everything gets changed to t. Come on, does this say that it's running? Get out of here. Get out of here. Go. Well, anyway. And so this would stay the same, but these need to be modified. There's my t. There's my t. So I'm saying, because this needs to match this, because if it's a vector of integers, I need to check it against a specific integer value, or if it's a short or a long. And so now the only thing that comes down to it is this should not build, or here we go, this succeeded. And that's not necessarily a good thing because I'm saying, oh, try to convert t into int. How about I use t instead? And so you can see, even with all that, we didn't get an error message. And this is still the same warning from earlier that it's not part of what we're doing. And so everything turned to t, but not everything, right? All this turned to t, but this is still saying an integer. And so that you'll still get the same result, 9, but now this thing is much more flexible, and you never have to write this code ever again because you have it. Give me a vector, give me a value, doesn't matter the type, and I will tell you an integer value for how many times you found it. I think that's pretty cool. All right, so the final topic of this, kind of like the last odds and ends before we push into all the data structures moving forward, an introduction to the standard template library. So the word template is a big deal. It's a vector of ints, sets of doubles, and so forth and so on. So it's a library that contains templated versions of frequently used data structures, algorithms, and collections, and you name it. And so, let's say, older compilers, how old? I mean, my goodness, it's 2020 at this point. So it's more of a challenge to find a compiler that doesn't work with the standard template library these days than one that does. So, okay, we're going to see all these. This is just a quick little high-level talk. So you're going to see all of this so many times over with vectors and double-ended queues and stacks and queues, and they're different, and lists and sets and maps and all sorts of other things, right? So those are the container classes, a class that stores data. The vector is the end-all be-all of all these kind of types. It imposes, and every one of these things imposes organization on the data in different ways, but we can access that organization, and we don't have to think about it. And again, we'll see iterators. We'll use iterators to be able to go through a collection of data, like a linked list, where data can be stored anywhere on your computer, but it's organized in such a manner that I can actually go ahead and link my way through and find that information and work my way with pointers to get all the data I need from my computer, from the memory, from the computer. And so there's containers, there's iterators, and there's algorithms. And so that whole Jesudas book, it's not 900 or 1,000 pages or whatever for no reason. There's a whole ton of stuff that works out. And say if you're a master of algorithms and using these data structures and containers and things like that, the standard template library is an amazing addition to your knowledge base, to your toolbox, because you could because a lot of the things you want to do in programming has already been thought of 1,000 times and already been implemented 1,000 times. So why should you reinvent the wheel when I could just use a specific function as part of this standard template library and then have it do the job for me? And it's going to do it better, it's going to do it faster, and it's going to take me no time to use it rather than all the time to write the code. Okay, so there's two different types of container classes. There are the sequence containers, so vector, double-ended queue, and list. Basically, that means that we can go one to one to one. Like you say, a vector is a contiguous block of memory, right? So I can access any element at any time, and just by figuring out a little bit of math, I can get to the memory address I need to. List, kind of the same way. If I want the fifth element, I have to kind of work my way to get there. But then that's different than the idea of associative containers, which basically organize the data and sort the data automatically as you're putting data into it. So that's a kind of cool trade-off. It's not always the fastest because it's all sorting, but when you're going to go search for something inside of this data structure, since it's already sorted, basically I can break it down and use a binary search in order to find data rather than a linear search if I'm looking for an unsorted data structure like a vector or a double-ended queue or a list. So again, all these different data structures we're going to learn have their positives, have their negatives, and it's all just based on, what am I trying to get across? What am I trying to do right now? And what is the fastest way I can use whatever data type to get me there? And that's essentially what this is all about. And so iterators, we will see in great detail. There are 4 different iterator types to go through basically a collection of data and iterate. Like for every int in a vector, do. For every double in my set, do. That kind of stuff. That's basically a fancy iterator to go through a collection of data and be able to push myself forward and backwards to the next element inside of there. And again, That's trivial for a vector. It's not trivial for all of these other data structures where data can be strewn all over the place and they're all linked together by pointers. The whole reason for iterators then is to make sure then all I have to do is try to increment it, and the code under the hood that knows what it's doing will increment that iterator and find the next value for me automatically. And so again, algorithms, we don't necessarily cover this in this course. There's a video, a 1 hour video on how to do 100 algorithms in an hour. And again, pretty powerful stuff, very powerful stuff. And once you're accustomed to this, maybe when you end the course, I really highly recommend spending a day or two watching that video and just practicing the algorithms that are part of the standard template library, how to use them with the collections. And the Jasudis book is perfect for that, because not only for C++, but as you move on to other languages, those languages have more built-in features, kind of like what you see here, completely different syntax, mind you, but the ideas are there. If you can do it in C++, you can do it in any language. So it's really a good investment in your future, trying to get hired, trying to get a job in the field, and just trying to be a better programmer, is to just kind of just suck it up for a day or two and just learn every detail there is to know about the algorithms and get the job done here. So like, say, binary search. We talked about that. We have videos for that. Well, now we just use the binary search feature, the algorithm inside of the standard template library. Random shuffle, and just minimal, give me the smallest element of a collection of data. I don't have to write that code anymore. That's why we have these things. I mean, once you're a professional, yeah, I know how to do them. Can't someone else do it for me? And that's usually where it comes down to. I can sort, and it'll use a better algorithm than that I can come up with. I mean, I can come up with some pretty good ones, but their sorting algorithm in general case is going to be perfect for my situation. And if not, I'll write my own. But generally speaking, sort is good enough. Whatever sort methods it uses under the hood to do its job, and so forth and so on. And again, this is just touching the tip of the iceberg kind of stuff when it comes to what the template library can do. But that covers this video. The important part here was, of course, the most important part here was the templating, even though it was a pretty short description here. But then we're just, in this course with me, you're only going to worry about a very small templating of a function. You're not going to worry about all the extra stuff you can do, that whole book of stuff that just melts your brain. We're just going to keep it to the level of just show me that you can set up a proper templated function when it comes down to it. So that's the major topic. Major topic 2 is the exception handling. And so we'll deal with that a little bit in this course too, because we need to, because of our last part 3 here, standard template library. All of this stuff that we see, algorithms and iterators and container classes and everything else that comes along, uses exception handling, uses templating. So we have to, that's why we talked about this for a half hour or 40 minutes or whatever this is. We at least have to have the basic understanding before we can jump in and handle all the rest. Because now, the rest of the course is pretty much just understanding the different collections, the different algorithms, and the different iterators that work with everything. All right, that's it for today. So my name, swardb@cod.edu. Great way to get a hold of me through email, or you can always comment below here on YouTube if I misspoke or if I said anything that isn't hitting your fancy and you're not quite understanding. Please always make sure I'm always available for you guys. Send me an email. I'll get back to you as soon as I can. And all right, moving on to vectors and everything else. It's going to be a good time. We'll see you then. See you there. Have a good one. Take care, everybody.